So we continue with the radioactive topic. And in this slide, we are going to be discussing on decay constant and half-life. So in sequence, we say that before we can talk about decay constant, we need to understand another parameter we call the activity of a radioactive element. So let's put down something for understanding's sake. We can say at an instant. So let's just write at an instant. Activity of a radioactive element. Activity of a radioactive element. The activity of a radioactive element is given mathematically and numerically as AC, which is activity sign, is equals to the N, the not N by the T. As you can see, the N by the T, which is also the same thing as what we call lambda N. So you need to keep this in mind, guys. The N by the T is called the activity of a radioactive element, which most importantly in your reactive material, you may see it in absolute form. So keep this in mind, guys. It's very important. That is the rate at which the particular is disintegrating at a particular point in time. So at an instant of time, the rate at which the radioactive element is disintegrating is called its activity. And it's written as the N by T, which is the same thing as lambda N. This lambda here, guys, is what we call decay constant. Decay constant. So always keep that in mind. Under the topic of radioactivity, lambda is called decay constant and not your wavelength. Similarly, the N here stands for what we call the numbers of undecayed nuclei. Numbers of undecayed nuclei. So these are things you need to keep in mind. So numerically, you can now try as much as possible to make N sub your formula. And if you do that from your mathematics, N will now be equals to, I say N, lambda, not N, guys. So if we try to make lambda sub the formula from there, what we have, dear students, it will give us nothing but we have the K constant, which is lambda, will now be equals to the N by the T in absolute value divided by N. So this is the definition we give to the what? The decay constant of a radioactive element. So the decay constant of a radioactive element is now defined with respect to activity and numbers of active nuclei. So when you want to write it verbally, it is advisable you say the activity of a radioactive element, you know, the N by the T, I told you is activity. So you can just write as the rate of what the rate at which was the activity of a sample to the number of active nuclei, to the numbers of active nuclei. So this is the definition we give to decay constant, which is very, very good for you to keep in mind in terms of questions that ask for definition. So now the decay constant is also used for the measurement of stability of a radioactive element. So another important thing you can also keep in mind is that the K constant in physics is also used for measuring the stability. So we say the K constant is also the measure of stability. So maybe we should write that as well. The K constant, which is lambda or lambda, the way you call it, is used for what's the measure. You can just say it's the measure of stability of a radioactive element. So this is also very important to keep in mind because you might see questions that ask you in terms of stability of a radioactive element. So you can see from the relationship I have set here, you can say that the K constant is inversely proportional to the number of active elements. So we say decay constant is inverse proportional to stability. So that simply means, numerically, you can now say it simply means if there is I value of decay constant, I'll just put that here, I decay constant, which is lambda or lambda, simply means, it means when you have I value of decay constant, it means that particular substance or radioactive element is less stable. We've talked about that in the previous slide about example of radioactive element and introduction to radioactive element and the decay equation. So now talking about stability, we use the decay constant. And when there is high value of lambda, which is decay constant, the particular radioactive element will be less stable. And when it is less stable, what it means is that you can see lambda here, which is decay constant, is proportional to activity. So if there is high value of lambda, it's directly proportional. It means that particular substance will have high rate of disintegration, or it will decay rapidly or very fast. But if it is what? Having high value of decay constant, the stability here, active nuclear here, it's going to be lowered, as in it is inverse proportional to this. So always keep that in mind that high stability simply means, or high lambda simply means less stability, and high, or let me say rapid, I think that is better, rapid decay or rapid disintegration. So keep that in mind. So the other one, if we want to write low value of decay constant, remains, now it be high stability, that is high stability, and it means let's say slow decay. So that is just what you need to keep in mind about stability, lambda, and what we call the rate of disintegration. So activity of a radioactive substance is inverse proportional to time. You can also see that here. So if somebody is asking you for a graph of activity, you don't need to disturb yourself. It's going to be an inverse graph. All this we've studied in our early classes. So the last one, because it's just a short video, it's half-life. That about half-life, because of due prep students, derivation is important, and the essence of this class is to help you understand those stuffs that you did not get very well in your classroom. So half-life of a radioactive substance. So I'll write radioactive substance as Ra substance. So let us quickly do this in this video, and we know we'll continue in the next slide for other things on radioactivity that we are still going to talk about. We have more of it. So about half-life of a radioactive element, we denote that by capital letter T. So now, to understand this carefully, because I think 2018, UPEP students were asked to derive this, and lots are complaining that they don't know how to derive half-life. Now, it's a simple thing. So if we consider a radioactive element, yes, students, we take a radioactive element, and if we consider radioactive elements, now let's say for a radioactive element at an initial time, that is when T is equals to 0, we consider the number of what nuclei at that point in time to be equals to n naught. That is, initially before it starts to disintegrate, the initial time was 0, and the number of what disintegration we take as n naught. So we now say at a particular time that half of the element or the radioactive substance has decayed, which you call half-life in your early classes. I know everybody can define half-life, and if you don't know, it is called the total time taken for half of a radioactive substance to decay. Now, here we say at that point in time, when half of the substance has decayed, we denote that as half-life, and we use capital letter T for the half. We say the number of nuclei that might have been decayed at that time will now be half of the initial value. We take it as n naught by 2. So now from here, we can say in sequence. So if we follow our decay equation, which we've discussed in the previous slide, so from the decay equation, I hope you still remember that, from decay equation, dear student, we can say, remember, n is equals to, I'm writing the decay equation, n naught e raised to power negative lambda by t. This is the decay equation I gave to you in the previous slide, and I was even able to explain to you how we come about this. And for those that are just joining us, you can watch the videos available on our channel on YouTube, Mosty Academy. So here from here, now we are considering the time at which half of the element has been decayed, we call half-life. So we substitute. At that point, n is now n naught by 2. So directly, I'm going to put n naught by 2 is now equals to, initial one was n naught e raised to power negative lambda, I said lambda by t, it is lambda t, please. This is lambda t. Sorry for that. So at that point in time, the time is now the half-life. So I'm now going to take that one to capital letter T. So please, guys, from here, from your mathematics knowledge, you can say lambda gets cancelled out. This is, I said lambda, n not get cancelled out. And what you have here is 1 over 2, which you can write as 2 raised to power negative 1 to show you all processes, is now equals to e to the power of negative decay constant, we call lambda, and capital letter T. From basis of logarithm available on our channel, we talked about this. We can always remove exponential form by taking natural log of both sides. So directly we can say taking natural log, which we call ln, natural log of both sides. So the work of natural log is that I'm continuing from this side. It will remove the e, which we call exponential. So please keep that in mind. So we can see minus gets cancelled out. You guys know that very well. So I'm taking natural log of 2 is now equals to, as you can see, the natural log will cancel out this, and we have e. I hope you are following this. We have e raised to power. I said e. E has been cancelled out. So we are going to have, here we have, what we have here directly is what we call lambda t. So this is ln 2 is equals to, you can see this has been cancelled out. When you take ln of this, you have e cancel out. So ln of 2 is now equals to, I'm trying to pick the marker. Oh, so we have ln of 2, yes, we can move, is now equals to lambda t. So from here, make capital T subject of relationship. So capital T, which is half-life, will now be natural log of 2 divided by the decay constant. So this particular formula is what we use in physics to calculate the value of half-life of a radioactive element whenever the decay constant is given. So please always have it at the back of your mind. And from your calculator, natural log of 2 should be approximately 0.693 divided by lambda, which is decay constant. So when else you see questions that gives decay constant and ask you to calculate half-life, this is the direct formula you use. And we've done some example on how we use the decay equation to get the value of decay constant. So in the next slide, we'll talk more about radioactive element, the remaining part of it. See you guys soon. You have a wonderful time, and bye.